Vinod sir, we can start.
Okay, sir. Good evening, all. It's me immense pleasure to welcome you all to the highly insightful ATAL Faculty Development Program on the future of quantum computing and high performance computing. Today, we are honored to have an accomplished entrepreneur and insightful technological innovator, meet Mr. Selvaraj V. Mr. Selvaraj is the founder and the CEO of Makes Lab, Make Vision, and Make Clouds, where he has been the forefront of driving groundbreaking innovation across multiple domains. With over 7 years of experience in tech industry, he has made a remarkable contribution in the field of artificial intelligence, virtual reality, and neural networks. As a prolific inventor, Mr. Selvaraj has continuously pushed the boundaries of technology, inspiring the next generation of researchers and innovators. Today, he will sharing his expertise on fascinating and cutting-edge topic, quantum computing, hardware, architecture, and components. Without further ado, let us warmly welcome Mr. Selvaraj V to take us on this exciting journey in the world of quantum computing. Welcome, Mr. Selvaraj, sir.
Yes, sir.
Sir, you can share the screen, sir.
Yes, sir. Sure, sir. So it is visible, sir?
Yes, sir, it's sharing.
Okay. Hi, good evening, everyone.
Sir, Terila, sir, screen, it's not
Tell
visible.
me. Not visible, sir. Now, sir? So it's visible, sir?
It is visible, sir. Go on to the PPT, just click on it, sir.
Yes, sir. Now, sir?
Now it is okay, sir. Now it is okay. You can proceed. Welcome, sir.
Hi, good evening, everyone. I am Selvaraj, and I would like to extend a warm welcome to all of you from various institutions and industries peoples. It's my great pleasure to have the opportunity to talk about the existing field of quantum computing and its hardware architecture. Today I will explain about that one. Quantum computing is a poison to many industries by solving complex problems that are beyond the reach of classical computers today's. Today, we will dive into the key components of quantum computing. So today I will explain about quantum computing and then some classical computers, supercomputers, hardwares, and then everything. I will give some basic explanations about that one. And you can get knowledge on about that one. And then quantum computing hardware also. I can give some explanations about qubits, quantum chips, and then control electronics, and then how the signals are collected, and then how they are analyzing. Like that, everything I will explain. And then thank you for being I'm here, and I hope this session provide a valuable insight into the fascinating world of quantum computing. So it was in a future, and then it will be give lot of solutions to a lot of industries, and then everywhere. The entire world completely changed after the quantum computing implementation in real world. So let's restart. So today agenda, I will give you explanations about introduction to quantum computers, innovation in quantum computer, and then hardware. My main topic is then a hardware architecture of quantum computer. I will clear give constructions, then how the components are they built on the, how they securely maintaining temperatures. So more thing I will explain about hardware architecture of quantum computer. And then I finally give some applications of quantum computer and finally conclusions. So introduction to quantum computer. So usually, you know, this is a quantum computer. This is a quantum computer. So definition about this one. Quantum computing is a field of computer science. It's a field of a computer science. Majorly, they use this quantum computer for various problem solving techniques that uses a quantum mechanisms. The quantum mechanism to solve complex problems. Uh, faster than classical computers. That is the main advantage of this one. Why we going from traditional computers to supercomputers to quantum to computer, which is switching over means because of we need to solve problems. In early days, we can think 1890s and 1850s and what happened means they computer they introduced it for calculating purpose only. Then after what happened after 100 years later in black based the computers are coming. The time the design was a huge size and then operating will be needed more power and then complex architecture designs. And then day after what happened after discovery of transistor in 1947 what happened the modern digital computer will be came and it will giving you a lot of application usage like that only. Nowadays, the quantum computer will be look like a big, and then it was a complex. After 100 years later, it will be look like a normal. Nowadays, how we computers looking like that, it will be look like a normal in a future. It will be give more problems to solutions. Majorly AI. AI will be rapidly grow faster while using of quantum computing techniques. And then key features here is superposition. What is superposition? What is the importance of superposition? Allows quantum bit to exit in multiple states. How will be it will be exit in multiple state? In traditional computer will work in zeros and ones, the binary logic. In a superposition, it will be possibilities. It will be outcome of the possibility will be more. How I will explain deeply superposition. Superposition is a fundamental concept in quantum mechanics that allow qubit to exit in multiple states simultaneously. So the probability of occurring chances are more on superposition. It can change any state, unlike classical bits, which can only be in one of two states, zeros and ones in classical computers. But qubit can be in a combination states. We can either predict it will be goes for the its own state, like a same time. This probability property enables quantum computer to process a vast number of possibilities, not a few numbers. It will be works like a vast numbers. So big numbers, it will be work. A vast number of possibilities concurrently, significantly increasing a computational power for certain type of problems. So, enlightenment. Qubits like became a linked, enabling faster information transfer. How it will enabling faster information transfer means quantum phenomenon. Qubit became interconnected, such that state of one qubit is directly related to the state of another. There is no matter distance between them. Enclave. This linking allow quantum computer to transfer the data and the process informations much faster than classical systems. The classical system goes lag on the processing times, but quantum computer not like that. The This linking allowed quantum computer to transfer and process information much more efficiently than classical system. Key driver behind the speed and power of quantum algorithms. That is the main advantage on there. I can say about what are the algorithms used. Yesterday, the Fatima explained about quantum algorithms and everything on that. So, as it enables coordinated operations across qubits. So here, quantum interface manipulating qubit, it will be manipulated. So we need to manipulation is needed here, manipulating qubit to amplify the correct result. How the quantum bit will be manipulated? I will clear explanation I will give on construction of hardware architecture. No, there I can give some video reference also, and then image representation I designed something, and then I will explain on that. Here I'm giving some quantum interface how it works. Quantum interface is the process of manipulating the probability of amplitudes of the qubit states. So, probability of amplitudes. We need to, here is a main important thing, amplitude. How will be amplitude working? How they amplifying? Generally, whenever you're going for analog, whenever going for analog data, whenever you getting a real-time data, the analog data we need to convert into digital data. Why that we know that one we are using for getting the informations, and then it needed to pass to computers. Computer need to understand. So analog data cannot be computer understand. So that time we going for analog data to digital data. That time we can use some resolution concepts and then ADC converters and some concepts are we were using that. Like that only here we mostly we use an RF and a microwave signals in hardwares. So in a quantum interface. Amplifying the likelihood of correct outcome and process incorrect ones. By leveraging the wave like nature of quantum states, quantum computers can perform operation lead to constructive interface, like amplifying the signals. There we can use Uh, there we can use amplify desired result, destructive interface cancelling out unwanted results. That is why the amplification process will be taking on this. This ability to fine-tune probability is critical for achieving accurate and different efficient solution to complex problems. So next, theoretical foundations of quantum computing. The theoretical foundations of quantum computing, early ideas. Who approached the early ideas? It was a great thing, I think. He introduced these concepts on the early days of 1981. Rich Feynman introduced a concept, proposed a quantum a computer to simulate the quantum systems. Uh, Nature is not classical. Nature is not a classical. How what they trying to explain on that means, for example, a quantum computer can process a large number of possibilities simultaneously. Make it much faster for certain type of calculations that not possible in classical computers. Later, I will explain how large number of data will be handled from Google, what they done, that things and I will later explain. Make it much faster for certain calculations, types of calculations that classical computers do. There is no physical limits for this quantum-based computers. So like this, they are saying nature is not classical. There is no limit for this quantum computer, like rules and regulations, like they saying. And then David, 1985, David introduced the concept of a universal quantum computer. So capable of solving problems which classical computers could not do. That's when they are approaching this theory on a theory of part of about quantum computing. These two peoples. So yearly experiments under milestones. Yearly my experiments like you can see uh, first implementations. They're developing a real-time hardware where they're developing means in 1990s yearly quantum systems used a nuclear magnetic resonance NMR to manipulate quantum states. Technologies like trapped ion and superconducting qubit emerged. How they are splitting and then how they are getting the data information from there, what they are doing, how they work means in what we have given it a trapped ion involve using electromagnetic field to trap individual charged atom ion. How they are trapping, that means that the ions are conformed and suspended in space using electromagnetic field inside specialized device such as known as ion traps. How they work? Qubits are encoded in the quantum state of the ions, such as energy levels or spin states. Lasers, I mentioned here, using laser to perform quantum computation. How lasers can computations will be happen? The laser can excite an ion, changing its state to represent a quantum one, and then another laser can cool the ion, returning into a quantum zero. It will be change the position laser lights like optical lights. So interactions between ions mediated by their mutual Coulomb repulsions allow for multiple qubit operations, essentially for quantum computations. So superconducting qubits materials, yeah, that is the main important because of I will give explanations about this one. Superconducting qubits use materials at very low temperature, exhibit zero electrical resistance. This is the main importance. Why we need a low temperature means you can go on traditional computers, classical computers needed coolers. Whenever process execute a lot of instructions at a single time means it will be goes heat. Then we can't get output optimization properly. That day we will use the traditional computers cooler, air cooler, liquid cooler, like that in other ways. Here also we using like that technique use like cryogenic liquid cool and all we using. allowing qubit to create and manipulate with a high speed. So next advantage. What is the advantage on here means we can get a faster outputs, a modern era and future outlooks. A modern era and future outlooks from theory to applications. How they are executed from this one means key points, main key points. In 1990s, breakthrough the algorithms. The source algorithm is a very important and efficient factorization algorithm. What we did we do means Peter Sohr in 1994. He designed to efficiently factorize the in this algorithm Sohr algorithm we factorize large integers and solve the discrete algorithm problem discrete data because of it was not a linear data, it was a discrete data. Whenever we going for discrete data means nowadays mostly we're using a machine learning concept to analyze the discrete data. Like that only in they are Peter Sohr in 1994 solved the discrete algorithm problem. Both of are foundational to many modern cryptography systems or RSA encryptions. So many encryption schemes RSA on the difficulty of factorizing large numbers. So algorithms undermine the assumptions and solve the problem exponentially faster than classical methods. So next one we can see for a faster database search, Groover's algorithm. So Groover's algorithm is in a very important year. Because of yesterday, ma'am also explained, Fatima ma'am also explained about yesterday lecture they taken about the Groove's algorithm. So one more time, I can remind that one what will be Groove's algorithm will do. So and then where they can use this one because of Groove's algorithm is a quantum algorithm developed by Lou Grover in 1996. So 1996. So what they done means provide a way to such an unsorted database solve unstructured search problems with quadratic speed up. If you go for a unstructured data means if nowadays IoT data center will be collecting in cloud. What type of database we are using means the MongoDB and that we use nowadays because of the data will be unstructured. If you go for SQL means it will be structured data. There we can fetch the data. That we can fetch the data that will be easy while going for the SQL database. If you go for MongoDB in unstructured data, fetching the information will be very complex. That time, the Groover's algorithm will be very useful to search the data and fetch the data will be very useful using this algorithm. In 2000s, experimental advances development of qubit technology, superconducting trapped ions, they are developed in modern era. And then Google only play an important role. 2019 quantum supremacy. What's the supremacy mean? They are attaining a maximum optimization while using of Google's Sycamore solves a complex problem faster than classical computers. I can show one video also about this one. 2019, what they done supremacy computers. I can show one video for you. Google you can see this one. This is a Google quantum supremacy computer. Supremacy performing see capture with a few seconds. So, would take a 47 years to complete one task for supercomputers. What Google did in 2019 with 53 qubit, it will solve within a seconds problem solving. This is a Google quantum computer. This is one major step forward for computing. And then Google, what they done means Google Willow. It's a state-of-art quantum computing chip introduced in December 24 this year. They introduced the one Willow. Willow chip represents significant advancement in quantum computing, building upon Google's previous quantum processor. How it will look hardware Willow means can show Willow. Google Willow. This is a Google Willow image I can show. So this is a Google Willow. What it be do means what are the key feature of this one means enhanced qubit count. Willow incorporate 105 qubits, superposing the capability of pre-desires sycamore. This increase enable more complex computations and improved error correction. They're using for the customers search algorithms. If any customer searching anything on Google means they need to provide accurate information. For that, the reason they introduced the Google Willow. So under few minutes, it will be calculated, will be performed. So a task that could take the most powerful classical computers can do years it will take to give the solutions. But going for quantum computers, it will be given a very short time information about everything. In future goal, what they say in application in cryptography and the optimizations of results and the material science, they can use these ones. Quantum computer. Ah. And then, see here, quantum computing will start an era of human progress, significant at the industrial and digital revolutions. So, healthcare. Mainly Astra in healthcare, the company AstraZeneca, what they develop mean drug discovery and personalized medicine. So, drug discovery. So, if any problem happen means any patient getting any problem, they getting on any new type of disease means they need to recognize the diagnose the problem, and then they need to give solutions for them. That time nowadays, what we using as doctors are using suggesting a machine learning based solution to them. In future, quantum computers can speed up drug discovery by simulating complex molecules and then chemical reactions more accurately. This will help researchers identify potential drug candidate faster by processing large data set and predicting how drug will be behave. If you know one thing, if you go for hospitals means if I'm saying some symptoms, I have fever, I have SpO2 level this, my heart range is this, and then I can give some symptoms about me means doctor cannot diagnose what type of disease he has affected. So that time they can give that symptom-based solutions for the patients. If you in foreign Western countries, what they're using means our countries, some people what they're doing means general medicine they will give. They can't understand the problem. They can't diagnose the patient's problem. They can give general solution for the based on symptoms. There is no personalized medicine. So if you're going for quantum computing based solutions, they can exactly diagnose your problem based on symptoms. A number of parameters we are giving, no, that basis they can give an exact solution. That's only the machine learning also say machine learning AI and all using that technique will be improved by using of quantum computer. And then see Merck company were manufacturing. In manufacturing, advanced materials industrial process. Merck uses quantum computing to design advanced materials. So see, if you go for an if you go for, if you an automobile, they will changing into aluminum plates, or they're changing into lightweight materials. If because of whenever you're going for an new thing, we need to introduce new material. We need to introduce. The scientists will do R&D on new materials. It will be take a much more timer. If I can say means if after the coming of carbon fiber material, it will be very useful for industries because of it was a lightweight. So if we're using carbon material for electrical vehicles means it is a light material and then strongest material comparing to steel. So that was one new discovery, no. So if you're using for quantum computer, help of with quantum computer, simulating the molecular interactions, we can analyze the material, that new material, how long it will be withstand. Like that things we can understand from manufacturing industries. They can use like this quantum computers. They can give a solution idea to the what type of material we can give this problem for, what kind of material we can give. Like that, it will be suggested in manufacturing industries. Like climate and batteries on carbon captures. This company exploring quantum computing for improving battery technology. So recently I saw Tesla carbon battery. They're doing R&D on that. Why they're using going for that type of material means Tesla they need to elaborate their EV vehicle everywhere. They're facing a current problem of battery power shortage. So what they're using means a lithium ion battery primary focus on that. So Tesla newest cylindrical battery format 4680, I think that's name battery cell name designed for the Tesla company. The Tesla company designed for higher energy density, improved thermal management, and a lower cost per kilowatts delivery. So they need to maintain optimization on thermal management because of nowadays see lot of Ola vehicle and then other some vehicles are fire accidents will be happening. So the company don't know why this will be happen. They don't know the problem on the climate and some malfunctioning were happening on electric scooter like that. They didn't know. But when you're going for a quantum computer, we can give these problem statements to that one. Means it will be fastly recognize and give the solutions for them. That's only they are demanding this one. So and then Rolls-Royce car company transportations. We can use the transportations for a quantum computing. So using quantum computing to improve automatic logistics. The Rolls-Royce, what they're planning to do here means automatic logistics by optimizing supply chain management and the transportation system. So because of they need to understand where the supply needed, where the demand is will be on there. That demand based, they need to give the supply for them. So this is the main reason they need to design. These enhance efficiency, reduce the cost, and ensure a smoother operation in logistics and delivery process. So these are the quantum computing they try to implement on that. These industries are doing. So and then one more thing, what can I say? Means investments. Different countries, how much they investing for quantum computing, computer making. So I'm given here data about Netherlands, 765 million to euro to 994 million dollars they are spending, and then Sweden, and then Finland. 24 million to 27 million they're spending euro on there, and then why these countries are why first of all what I'm asking trying to ask means see India 73 billion to 1 billion the amount spending. European country US US how much spending means 1.2 billion amount is spending. When means this data means global effort 2022 approximately estimated amount spending means 30 billions of amount they are investing to develop a quantum computer. This is the biggest thing. Nowadays, what they're trying to make means AI. Every country before 60 to 50 years, the country will be fighting for nuclear research. They need to dominate in nuclear research. So they are focusing on nuclear weapons. Nowadays, what they try means they need to show the technological development on their countries for an AI implementation. After some few years, every country will give importance for quantum computer implementation. We can ask why they are investing that much money. What they need to recognize in this real world. How can after investing the money they will be getting really benefit on that? Yeah, obviously they can get benefit on that. How they getting benefit on their means the people's for people for this can suggest a drug discovery for any disease like COVID disease happen means every country will be suffering. That time this will be helpful. Quantum computer based we can go for solutions. It will be helpful. Climate modeling they can clearly predict the climate conditions. Financial optimization they can increase the GDP while they're giving financial inputs to the quantum computing means it will fastly recognize the financial improvements like for they can improve GDP values for the countries. And then advanced cryptography they can use this technology on their rising demand. Nowadays the rising demand for industries like finance, healthcare, logistics will increasingly adopt quantum solutions. They need to change it. Nowadays they're going for machine learning and AI deep learning solutions. In few years, they go for an quantum based solutions. The quantum computing have a big market, growing market values like 500 million to billion value market it have in 2013 it will nearly reach 10 billion of more than investments on there and then is many government and corporate companies are work on these projects. Nowadays it's like Google, IBM, Amazon, everybody working now. IBM are working for a cloud based quantum computer. They are working Google using for their own search engine algorithms and then data retrieval for that reasons they are working. So so how much they amount they're spending? See here I'm given a clear timetable for that investment in quantum computing. So Google. See, the company Google estimated investment in quantum computing 1 billion since 2014, over 83,000 crores. Superconducting qubits quantum algorithm and quantum supremacy. So they need to achieve that one. See, every country, IBM 2 billion in 2010 itself, they're spending for IBM. It was a good idea, I think, because of they can give IBM can give the cloud based clients they can give solutions for that easily. Because of IBM, I think it will be have a big opportunities. In early the 1960s, IBM introduced a computer processor and everything. After they have a huge break, it was a great comeback while discovering this one cloud-based cloud-based quantum computing is a good idea, and then they can give optimized solutions for client, the cloud-based client users. So Microsoft since 2017, how much they spent means they spent 1 billion amount for a quantum software development, topological qubits. The software development itself, who spent means spent. Microsoft spent quantum software developments, and then Intel company, Intel company. Uh, 100 million annually they spending for superconducting qubits, quantum hardware and development. So they develop investment doing for Intel companies on quantum hardware also. So and then Honeywell company 100 million since 2020 they spending trapped in quantum ion computing and then quantum computing services, D-Wave, 50 million, and then quantum handling and quantum optimization. Alibaba, really Alibaba company, the Chinese company Alibaba, spending quantum cloud computing and quantum software. They're spending amount on their Richie quantum computing, 40 millions of amount they're spending for because of discovery of superconducting qubits, cloud-based quantum computing. So the highest investment, the see, this was really a good thing. In the highest investment, IBM over 2 billions of money they spending, 2 billion money for IBM has been one of the leader in quantum computing with long-term investment in both hardware and software. Because of it, really good. Because of some companies are some implementation like Alibaba are doing software only. Cloud computing and software. Some companies doing importance on the software parts only. But IBM are putting efforts on both hardware and software implementation. Because of like that doing means they no need to demand any other companies. So they have own itself everything. They can give up best solutions for that in cloud infrastructure they're making in quantum based means it will be good. And so lowest investments we can see who means Alibaba over 50 million like Indian rupee 1000 to 250 crores. Alibaba quantum investment, although significant, is the lowest among major companies listed, primarily focusing on quantum. They will be in future they can invest. We don't know. Okay, next. So, which companies are state of quantum computing? So here I'm diagram given. What type of means a superconducting, topological, and then optical. These are the technique use. The state of quantum computing. The first quantum computers are for quantum supremacy still in progress. They need to achieve a supremacy. Do you know what is supremacy? Supremacy means the hardware need to perform perform maximum optimization it need to do. How I can say means Google achieved that one. Quantum computer can perform specific task faster than the most classical computers. Even though the supercomputers cannot also do that thing that can be achieved by quantum computer. That is to be called as a quantum supremacy. Um, the key points. What it is in a benchmark you need to create. Benchmarks are often highly specific computational problem designed to highlight the capabilities quantum system rather than real world applications. So here I got one thing I got to tell us milestone quantum supremacy means Google achieved one task. Later section I will say about that one what means sycamore process what then like that I will explain. And then see here superconducting Google, Intel, and then China, Amazon, they are a superconducting material they are designing. And then topological, Microsoft QTech designing a topological, optical based technology they are developing China, Xanadu, Orco computing, color centers, quantum brilliance. These companies are working for an quantum based technologies, hardware, software, everything they are giving solutions. So the most of the quantum computer from companies like Google, Intel, and IBM are using gate models of quantum computer. The hardware they are focusing, hardware and some software also they are focusing. So state of quantum computing. On the other hand, companies like D-Wave and then TQ are using quantum annealing, which yields quantum inflections. They are designing for these companies like D-Wave companies are developing a low energy state of hardware they are implementing. So the energy also a very important thing because it can get a kilowatts of voltage power that it be consumes. They need to consider about energy also. This they are focusing this area they are focusing. So this is one of the Google in quantum computing developed a Sycamore quantum computer that demonstrated quantum supremacy in 2019. What will be done means focus on superconducting qubits, which are tiny circuit cooled to near absolute zero. Why they need to do means this one they developed a Google Sycamore developed a 54 qubit superconducting quantum computer. What it will do means the task is what means random circuit sampling, random circuit sampling. This one what you need to do a random circuit analysis need to do. The task is computationally demanding um, but demanding because it involves similar to the bigger of quantum systems, it will generate a random numbers. So it need to give a one solutions like Sycamore completes this task in 200 seconds. It will nearby 2.5 minutes. What it be done means Google estimated the same task doing by supercomputer means it take a 10,000 years. But while using a Sycamore 2009 achieved within a 2.5 seconds itself, this is called as a super mercy they saying. Still in future, it will be a lot of implementation on that. Solve problem faster than classical computers, like optimizing process or modeling of molecules. Here I am given that I demonstrate quantum supremacy in 2019 by solving a problem in 200 seconds. That could take classical computers 10,000 years. Goal, what the goal means, solve complex problem faster than classical computers. Process optimization, this is the main thing. Process it need to optimize, making system more efficient. Whenever we efficient is necessary, we need to give more efficiency. The molecular modeling, accurate drug discovery, and material design. This is the Google are designing. So IBM in quantum computing created by the IBM quantum system one, the world first integrated quantum system offers the cloud. They offering a cloud services nowadays. The free cloud services. A lot of people, Google also giving a free cloud services. You can know that Gmail also giving 15 GB. If you go for OnePlus means Google OnePlus means they're giving a premium for 100 GB, 1 TB like that. They're giving. So like that in future, IBM also given a cloud-based space for the clients. So focus on building scalable quantum systems and advancing error correction to make quantum computers practically. So they're giving these solutions. Why means they get the people can use the clients can use in a quantum computer from cloud itself because we can't do that building hardware. So the IBM built on a hardware. They're giving it into a cloud-based services. It was a good idea. So other key players, Amazon bracket, they also developing softwares like that, quantum based solutions, quantum perform parameters like IQ, Rigidity, D-Wave, Microsoft Azure, supporting multiple hardware backends, D-Wave system, pointers of quantum annealing, specific optimization problems, IonQ, developed trapped ion quantum computers with the high fidelity qubits. So future directions in quantum hardware. Here, I can explain that the hardware ports and how it will be changed. Then what are the necessity? Everything I can explain. Scaling quantum hardware, modular systems, connecting multiple smaller quantum process to work together, creating more powerful systems. They need to maintain a room temperature in a certain level. Because of whenever the environmental interrupt on there means it not work properly, it will be disturbed. They need to make separate allocation for that one. Quantum hardware became more accessible. Quantum as a service, more platform like IBM Quantum Cloud, Amazon Bracket offer cloud-based quantum computing for business and researchers. So they given these solutions for the who means the business developments and then researchers. They given cloud-based solutions on that. Growth of quantum startups. New companies are constantly developing new quantum technologies, accelerating their progress. They need to implement on that. So next I can go for an here I can give some here onwards, we go for some hardware explanations. I will explain some traditional classical computer hardwares and then quantum hardware. So because I give some basics about the traditional classical computer hardware. So here key concept is a binary logic, use zeros and ones to present and process the data. So core components like input devices like keyboard and mice, and then CPU execute instructions using logic gates. In quantum computer, completely different. So and then memory, RAM for temporary data, storage for long-term data, HDD and SSD. Nowadays, HD and SSD, and then we are using an M.2 NVMe based hard drives are we using. Sir. So output monitors and printers. This is what means classical computers having this components, hardware components. And then if you go for an quantum computer hardware means the key features, principles, present data in superposition, zeros and ones simultaneously. And then quantum alignment qubits are interconnected, sharing their states. And then interface, enhance correct solutions, cancels and errors. And then core components, quantum processor perform operations on qubit. How they controlling? The controlling technical they use mostly for an microwave signals. See here I can give some this is superposition state. They can be actually any state can attain any time. Control system user lasers, microwave to manipulate qubit. Cryogenic system keep qubit stable at ultra low cold temperatures. I can explain this. Cryogenic systems. Why they are using a cryogenic and all? I will show in architecture design. So we know usually this one quantum versus classical computing. So once yesterday itself the faculty will be told about this one already. They are told about these basic things. Once more, I am reminding this one because of we need to remind this one because of we going for a hardware part. No, that's what I am explaining this one. Classical computing information proceed using a bit that is zeros and ones. Quantum computing uses a qubit that already we know it will be multiple state will be attained a single time. So components of quantum computing hardware, physical systems used to represent qubit, atom, ion, superconducting circuits. This is an given example. This image you can see means you can understand how it be the quantum computer can position will be happen like this image you will see means you can understand. A quantum processor, the core component where quantum computer computations are performed from this technology. So here one more thing I may explain for an hardware part. Why cooling is essential for processor? I'm explaining about classical computers. Why the cooling is very important. Here is the processor. Integrated processor is here is the processor. Like you can think this is an Intel processor or AMD processor or any processor. In mobile also it have like a Snapdragon, Qualcomm. They're using a processor. No, above they use an thermal conductivity and then a cooler they will be placed the heat sink. Why they using this one? Why I'm explaining this one means first of all you understand this hardware architecture and then cooler everything understand means while going for an a quantum computer how they using technologies they will be maintaining absolute zero temperature in a quantum computer then only it will be perform better. So that we need to understand now. So I'm giving basic about classical computers coolant system. Then after I can explain that also. So here what I'm saying means prevent overheating, reduce risk of damage and system shut down due to excessive heat. Whenever performing more complex numbers data analyzing or any doing output means it will be goes heat. The processor will goes heat. That time we need to cool the processor. The maintain we need to maintain the temperature. So if you not maintain means it will be what happen, it will be process will be hang, system will be happening. No, nowadays you can see laptop will hang, mobile will hang, system will hang. Reason because of the processor will be in a heat state. That will be what happen means it not give a optimized solutions. That only we need to processor we need to keep in a cooled. So in case and then main benefit increase lifespan. Keep the processor cool to avoid long term damage and degradation. And ensure stability, prevent the crashes, errors, and instability caused by overheating. You see, people will think whenever the processor getting heat means the system will hang. They think system will be problem, not problem. The processor will getting heat because of it will be hanged. Reason this is overheating. So how they we are giving a solutions means cooling in a normal computers purpose keep components like CPU, GPU and motherboard at a safe operating temperature. See here is the motherboard, then here is the heat sink, here down is the what means the processor. Like you can think Intel processor or AMD processor, any processor you can think. This is an heat extractor. And then here's the radiator. Here's the CPU water block will be there. And then this is an SMT components. So we need to keep the processor in a cool. So how they doing means I will explain. Temperature range operate around 20 degrees Celsius to 30 degrees Celsius should be room temperature. So because if you go for 50 degrees Celsius, we can keep the system means the system will cannot work properly. It will be act malfunction will be happen on there. So that time we need to maintain 20 degrees Celsius to 30 degrees Celsius. So cooling systems are designed to maintain this temperature range and prevent components from reaching unsafe levels. So then only it will be work properly. I can give some explanation about the different type of cooling systems. So cooling method in normal computers, air cooling. This is an processor. This is an exhaust fan. This is an aluminum based heat sink. Okay. A fan draw air over heat sink attached to component like the CPU and GPU. Heat sink help dissipate heat from the components. Fan help move the hot air and then it works smoothly. So liquid cooling, liquid this is a air cooling based concept. Exhaust fan will absorb the hot air, but in liquid cooler this is completely different. In liquid cooling, a pump circulates a coolant through the tube that passes overheated components. Here they can pass a water. Here they can pass a water. This blue and red pipe is there. No, there they can pass an water. One pipe will be pass the cooling air. One pipe will collect the hot air because of they need to keep the process in cool. So this technique they are using the heated coolant flow to a radiator where the heat is dissipated and the cooled liquid is circulated. That time it will be maintained a proper temperature on the processor. That only they are using these two techniques for classical computers, air cooling and then liquid cooling. So in quantum computer, we use a cryogenic. That will I will explain. So here the main topic we came now. This is the main hardware architecture of quantum computer. Here I can explain a major four blocks in hardware architecture of quantum computer. A classical computer. This is see here this block is a classical computer. This is a microwave electronics. Here the amplification, digital signal processing, and then everything will be working here only now. And then here is the quantum computer is a quantum computer, and then here is the dilution cryostat will be happening here. This a chemical will be here placed. So in first in classical computer what will be do means control software is used to generate a digital signal for the manipulation of the qubit state. So it will be collect the data from the microwave electronics. This is classical computers to identify the state of qubits. The output signal is processed and analyzed. See here I am given two color variations for this one understanding. Input signals are in a green color. The input signals are passed to from classical computers to microwave electronics. This is an amplifications and all will be here only done. This data will be passed to where means a quantum computer. And then the quantum computer, the quantum chip is here. It will be give some informations. It will be again coming back to the microwave. Here amplification, filtrations, everything will be happen in here this part only. Then after it will be pass the data information to here. So this is another, they need to maintain these compounds of what it be do means the processor need to maintain a minus degree Celsius. They need to very cool. They need to maintain this processor. So they're using an helium 3 and helium 4 dilation cryostate. So what it will be do means this third block what it means the quantum processor and the peripheral compounds are cooled down to few millikelvin to shield the qubit against the influence of thermal radiation because they need to maintain this process very low temperature. It was a very lesser than freezing temperature, minus degree Celsius, like a millikelvin they need to maintain here. So then only the process will work because of we working on atom, ion, no particles, no. That's only we need to maintain that much lesser temperature we need to maintain. So and then fourth is a quantum processor. The quantum processor, this is the actual processing unit containing a qubit, couplers as well as control and readout lines. Okay, I given you see completely. I'm giving the hardware architecture of quantum computer, a classical computer, microwave electronics. I can give a brief explanation about this one, and then this one is an quantum the computer design, and then this is a chemical reactions will be happen. Next slide, I can give some ideas. See here, classical computer, a role. What is the role? Act as a main computer, act as the main computer, main control system. Whenever the quantum computer give information, so you need to collect a function. What is the function means? Generate a digital signal that control the state of the qubit in the quantum processor. So, strength of a classical computers here means what I can say is the strength of the classical computer means it need to perform input and both it need to understand. So, general purpose computing is suitable for wide range of tasks from simple arithmetic to complex simulations. That only do classical computers. Here, what it be do means supported by a matured hardware. It based mature hardware and software. Basically, the ecosystem it need to support, and it need should have a predictability and stability. Perform complex operations. So it will be perform complex operations on that. That will be understand for the classical computers. Limitations of classical computers. So what are the limitations of classical computers? Which we can say grow exponentially with the size of the input. Whenever giving a big data of data again means it will be or operation of the classical computer will be becoming difficult. And then power and energy consumptions. Scaling classical system often increase the power requirements. It will be give more heat on there. That's also classical computers problem will be facing on there. And then inability to harness quantum phenomena cannot sufficiently simulate or leverage a quantum mechanism for computations. So that the problems are happening in here in the classical computers. Key points about this one means classical computers interact with the quantum system to provide input signals and interpret the outputs. So this is the microwave electronics. Once more I tell you, where is the microwave electronics means here the microwave electronics. So this is the microwave electronic part. Once more I'm showing this is one of the microwave electronic part. The digital signals are converted to analog signal. Electromagnetic pulses at a microwave frequency range. This will give a microwave signals. That means a microwave or radio frequencies. That will be collected from here. That variations will be collected. Here they can use the sensors also. That will be the calibrated data. The calibrated data will be again analog data will be converted to a digital formats. From here the conversions will be happen. How it will be working? I'm here explaining. Microwave generators how will be working in a what is an IQ mixer? IQ mixer in microwave electronics they use an IQ mixer, a device used to modulate and demodulate signal by combining combined solutions. Generate a signal with precious frequency and a waveform for qubit control and readout. That is just two signals. Precious frequency and waveform they need to create I signal in phase, Q signal quadrature, 90 phase shifted. So here we need to do a cryogenic amplifications also. Quantum system operate at cryogenic temperature. Microwave signals are amplified with the minimal noise using amplifications. There will be resonators also. Microwave interact with the qubit resonators which is diagnosed to match specific frequency and achieve strong coupling. This is only they can achieve strong coupling. So how it works means input we need to give microwave and RF signals are carrier. base band signal in phase and Q quadrature. So, so processing a I signal modulates the RF carrier directly. Q signal modulates the 90-degree phase shifted RF signals. That here the amplification, the processing will be the two signals are carried out on there. Whenever there is, they need to match. They need to match this one because of amplification process. Output what will it do means combined signal encodes amplitude and phase informations. So see here. Microwave electronics purpose converts signals between classical and quantum formats. The main performance means it will be bridge intermediate. It will be act like an intermediate bridge for quantum computer and then classical computers. Here we can so use frequency range like ultra high frequency means 300 megahertz to 3 gigahertz range. If you go for extremely, we need to this micro can generate a waveform like extreme high means a 30 gigahertz to 300 gigahertz also they can generate a wave like a high pulse waves and then the q pulse waves so they can work on there also. And then if you need to understand about this wavelength means electromagnetic wave exhibit short wavelength yeah, because of electromagnetic means here we can say a radio frequency RF. Do you know the radio frequency? In the radio frequency, we're using a lot of technologies. Wherever we're using radio frequency technology. In cellular mobile communication, we're using a radio communications only, like TDMA, time division based multiplexing, CDMA, carrier division code multiplexing. So here this technical we in our LTE and H techniques are we using for mobile communications. And then if you know RF, no RF basically 5G and beyond development of 5G technology. The most uses in the RF waves only. In like that only in quantum technology, increasing use of microwave electronics in quantum sensing, computing and secure communication will be happen. So they are using a microwave or RF radio frequency. They are using advanced material, gallium, and then other materials they are using. So how it will work? I mean, convert digital signal to analog signal. Because of when our computer given a digital signal, but micro signals are getting the informations from where means we getting the informations from a quantum computer that will be trigger the some microwave frequencies that will be collected from the microwave electronics to control the qubits. They need to collect the qubit data from microwave only. After computations, convert the qubit a weak output signal back into a digital data. That weak data, the weak data we need to what we need to do amplification we need to do for amplification purpose only we using an I pulse and Q pulse. These two pulses will what will be do means it will be amplify the signal. So key component, the interface bridges classical computer and the quantum processor. It will be act as a bridge. The microwave electronic act as a bridge. Here the I pulse and the Q pulse are given. So what will be the mixing of these two signals? So what will be give means it can see 90 degree phase shift quadrature signal will be happen or like that. So if any signal will be lost on there means it will be match the signal to the Q pulse. Finally, what will be there will be summation will be happen and then everything will be calculated and the output will be we will get. So the microwave electronic what will be do means it will be act like as a bridge for classical computers and then quantum computer. So next slide we can go. A dilution cryostate. Dilution cryostate, what it will be do means it need to maintain a temperature. It need to maintain a temperature at a millikelvin. The maintain quantum processor and the other component at extremely low temperature only it will works. If we didn't maintain a low temperature means it not work properly here. So it need to avoid thermal noise. So and then environment variations. So reason quantum operations requires near absolute zero conditions to prevent thermal noise and maintain coherence in qubits. So a dilution cryostat shield qubits from thermal radiations. The technologies see use of mixture of helium-3 and helium-4 to achieve ultra low temperature. I can give some pictorial representation for this one. Then you can understand more things on there. So see, here I'm given this design I done for this presentation. I done this hardware design. So here you can understand the hardware, how will be working inside, and everything you can understand here. So here see is a GM plate. You can you need to see this GM plate. This design where I can show means see I'm showing. So what this design means. So this is a what this means I can show in this video. This only. So this is the GM plate. GM1, GM, these are the GM plates. Here down only the processor will be on there. See, this is the quantum computer. So this is on the chamber cooler. So see once we saw no. Ah. So this is GM. You saw no that golden disc plate. This is that is a GM plate. This is under the GM plates. So what will we do means initially it will be in 24 Kelvin, 24 Kelvin and 22 Kelvin. Thus, thermal stages maintain at a higher temperature compared to the rest of the system. This Gifford McMahon cryocooler provide initial pre-cooling to bring the system down to around 24 to 2 Kelvin. This will what like initially in 24 Kelvin. No, that time what will be happen means these two mixture of chemicals, what means helium 3 and helium 4 will be mixed here. The cryo pump with with the heat switches. The cryo pump, what will be doing? Yes, here the cryo pump with heat switches. The cryo pumps are used for condensing and circulating the helium 3 and helium 4. What will be using means the heat switches allow thermal isolations. It need to isolate the thermal. It need to reduce the temperature. So T and H, what is the T and H means? T is a temperature indicating, H is a heating element indicating, and then like a heat based indicating. So enabling efficient cooling transition between components. From this, what it will be do means enabling the cooling for an processors. So cryo pump will be heat switch. It will be act like a heat switch. See here, first GM before sheet 24 Kelvin were coming, and then after coming the mixture of helium 3 and helium 4, the temperature level will be completely decreasing 24 to 2 Kelvin. Okay, so next so ensure the here is a one component, a major component, a film breaker. A film breaker. What it will be do means ensure the separation of this. Here two chambers are there. Here two film break chambers are there. First film break chamber. What will be do means separation of this separation of helium from the system. When it reaches a mixing a chamber, maintain proper operation of the dilution refrigerator. It's like a refrigerator. It will be cooling the system. The film breaker one will be separately connected to helium 4, and then next one is connected to helium 3. Both will be separate, the helium 3 and the helium 4. Then when here come on here in this GM plate come the lower temperature below than 1 Kelvin. It will go now only it will go to an milli Kelvin range. So after the millikelvin range, here will be an when coming in of 500 millikelvin, the cooler will be passed to the mixing chamber. So here will be the mixing. Here the separately the mixing because of see here coming in a 1 Kelvin range of temperature. After they are separating separate chamber film breaker chamber. So the data will cooler will be going here, and then there is a mixing chamber. The mixing chamber what will be doing both helium and helium 3 and helium 4 they are intermixing here. Here what will be happen means they are attaining a very low temperature like 50 millikelvin to 100 millikelvin range. So this is the main reason. So they here itself the mixer itself it is applied here to drive the helium into mixing chamber. This is the core of the setup designed to reach temperature between 50 millikelvin to 100 millikelvin. Then only the processor will work fine. Before I told no, in classical computer, whenever heat exhibit on a processor, what will be happen? The malfunction will be happen on the processor. So he will here also like that only. The quantum computer we need to maintain a very low temperature. Then only it will be work fine. A purpose, yeah. What the purpose? The system is primarily used for experiments requiring extremely low temperatures. So this is the main reason. Quantum computing research, low temperature physics experiments, examples studying superconductivity or quantum phase transitions, precision measurement of physical properties. So these research purposes are they using an quantum computing, low temperature physics experiments like on a superconducting material. We doing an R&D on there means we need this type of cooler systems like GM plates and everything we needed. And then precision measurement of physical properties. Any physical properties we need to measure means that time we need this one thing. Sir. And then is the quantum processor. So you can see here the quantum processor. So you can see this quantum processor. It look like a traditional processor. Here there will be an qubit operation will be performed here only here, unlike in classical computers. So this will be solve complex problems. They can give in a faster solutions. So and then quantum processor architecture wow, we superconducting quantum processor IBM Q and Google Sycamore that are developing on their projects. So here I'm given high-speed digital and analog signals. So quantum classical interface, topological qubits. Topological qubits, what will be do means it is given a technology to data drive the cryogenic controller. So they need to maintain this room temperature absolutely minus degree Celsius after they implementing a software solutions like image processing and the data mining and then large data of analyzing predictions, anything they can develop a software course on that, and then they can use like an applications for any problem they can use these applications. So this is the architecture of the overview of the softwares and hardware how they interconnected are there. So and again, one more time, I'm explaining quantum interface. You know already, this is a mapping to amplify the quantum correct results. And then superpositions already I explained. The bit can either any is proposition state, enclosement. Quantum is when two particles become linked, state of the one more in affect the other, even they are apart. The strange connection happen faster the speed of the light. It is a key feature in quantum computing and challenging classical futures. So see here the entire complete hardware architecture. You can see here the architecture designs of this one. This is a quantum computer hardware system. In video, you didn't see this one a chamber, enclosing chamber. You didn't see because of inside part only I showed in that video. Once more, we can see that video also. So I can show some IBM what they're doing, and then so this is IBM doing. This is the IBM company. See this is share. So what I've explained, no, this is an shielding chamber. See here is the GM plates. Here are the GM plates, and then cryo pipes are here. The cryo pipes are here, and then the helium mixtures are here. It will be helium mixtures will be in here, and then finally see here the they maintain here only absolute temperature like 50 millikelvin to 100 millikelvin. So then the process will be there. They are IBM showing their quantum processor for public showcasing there. And then, so see this is the design. So they need to order the one more time. All we can see this on everything. Johnson junction, the tunnel junction between superconducting and the electrode, which make the LC circuit non-linear and turns into a qubit. So this will be an not a, it is a transistor. It will be in a super junction on the inside of the quantum computer. So superconducting qubit. Superconducting qubit is the smallest unit of quantum information along with control and readout lines, and the design will be like that only. If you need to understand this about means we need to go for a VLSI design. You have knowledge about VLSI designs, very large scale assembling. No, that we need to understand means you can understand this one clearly. So and then quantum processor QPU. qubit and coupler together with the readout the resonators and then a control line from the quantum processor. This will be here will be they designed a very tiny. It will be, we can't see this one. So this is the main thing of here means a vacuum can. This is a vacuum can. The vacuum can is the outermost can which protect the system from environmental and influence heat transfers. It will prevent the environmental any problem, natural heat exhibiting outside no environment. It will protect the environment from this chamber. A microwave amplifier is here. I explained no electronic microwave amplifier. So analog to digital converters. I'm explaining no before that one will be happening here only. So this weak output signal is amplified by several orders of magnitude before it conversion to a digital signals. So in here they can maintain a 4 Kelvin 4 Kelvin stage. Here only one every this GM plate graphite plate I told no this graphite plate one two three four after these four plates the temperature will be 4 Kelvin to 50 millikelvin to 100 millikelvin they maintain here itself. That's why I'm giving this one everything still stage cold stage dilution units. Dilution unit is a very important unit here. Dilution unit because of dilution unit what it will maintain means the main part of the main part of the cooling system where the two mixture of two heliums, helium 3 and helium 4 isotopes undergo a phase separations. So here the main important, the two helium mixtures can be do it became a helium will use a very low temperatures. So it will be attain a millikelvin. So and then here the isolators isolate the qubit from noise and let them signal pace without any attenuation. You do know no, attenuation. No attenuation is then we can attenuation using y means calculating the processing the how much we give an input given how much we getting the output that will be calculated by attenuations only. Chaos shield double layers chaos shield protect the qubit from external magnetic fields. Any other external magnetic disturbance coming for this one, it will be protect from the electromagnetic, which one is cryo shield. So and then input cables are here is connected every you need see in video no input cables. So that input cables the input signal reaching the qubit its attenuation by several orders of magnitude to suppress the thermal radiations. So and then finally here the quantum processor will be here placed. So this temperature and then connectivity everybody made for the quantum processor need to perform it need to optimize their operations. So this is the quantum computing hardware architecture, and then these are the main major components. So and then we can see application of quantum computer. Applications of quantum computer. So in future, how they are use this applications of quantum computers means for database searching. In initial itself, I told database searching. Databases when in yesterday, told one ma'am told what means Grover's algorithm that we can use here itself. Grover's algorithm we can use here. Imagine you have a database of Aadhaar card number stored in a system. We can consider India. India nearby 150 crore peoples will be in India. Everybody, other data we collecting a one system. We can consider as a supercomputer also. So you want to find a specific Aadhaar number. So you need to find a specific person in India using classical computer or supercomputer. It will be very complex. You could have to check the each record one by one. It will be time consumption very high, which could take a lot of time for a database search. So if we go for in a quantum system using Grover's algorithm, we can fastly fetch the person in 150 to 150 crore people in India. No, we can identify any particular person means from other data we need to recognize the person means using for Grover's algorithm we can easily identify the persons. So we can use this algorithm for a big large data based recognition, data mining. In data mining, under this concept we can use in quantum computer based solutions we can give. So and then one more and then one more applications in artificial intelligence. In artificial intelligence nowadays what we facing means in data modeling. if I can say, if any in industry, so what we're facing means, if any problem I need to recognize, if like I can what I can say, recently one project we doing, what means project means in artificial intelligence, fault recognitions. Whenever I can give one solution giving on company to like a medical based company, that one is they're manufacturing medical bottles, that are bottles. They need to identify properly seal the water can tap and then structure of the water can, everything they need to identify. If in initial time we need to develop a model for image recognition station, we need nearly 10,000 to 1 lakh images for precision recognition. That time our classical computers, what will happen means, the classical computer take a time like 10 days to 1 month for large data of image. We training, no, we need to do annotation and then we need to label it one and then we need to train, means it take a much more time. While I'm using, if I have quantum computers, it will be easier. Like training a 1 lakh data, 1 lakh images, it will be easier, and then I can give a customer to fast solutions. Because of in the future, if you have quantum computers, that will be easy. So that's why I'm suggesting quantum computer. Why need a quantum computer? For like image recognition. In image recognitions, okay. If you go for video analytics, it will be take much more time. So we need to process fastly. So that and all we need a quantum-based solutions. So here what I'm given means, quantum computer can enhance crime investigations by using AI for faster face recognition from large image database. So if any, we can consider one scenario, any person thefting a vehicle from anywhere, whenever they in front of CCTV camera, the CCTV camera cannot recognize the particular person because of India have 150 crore people. The particular face they can't recognize. If you have a quantum computer means, you can recognize fastly that crime person, fastly. So because of that much database, it can easily analyze. That's only we need a quantum computer. So this enables quicker, this enables a quicker and more accurate analyzing compared to the traditional methods. So and one more thing is weather forecasting. In weather forecasting, quantum computing can improve weather forecasting by processing a complex simulations of the atmosphere much faster than classical computers. So we can give input data like temperature, humidity, and then previous year's data, last month date data, everything we can give means, if we give large number of data means, classical computers what will be, it will be suffer. If you go for quantum computing, it will give precision solutions for weather forecasting. So next, simulation of chemical reactions. These situations will be happen 2019 in COVID time. The doctor cannot give solutions for COVID patients. For they need to detect the vaccine for COVID virus. So the time the most of the people will be went to machine learning based solutions. So, in case of coronavirus COVID-19, quantum computer can help simulate the chemical reaction to understand how will be virus interact with human cells, or how different molecule like potential drug might affect the virus. Like that, we can do R&D on that, and then we can give a faster solutions. By using of quantum computer, we can give a faster solutions for the that particular disease. That's why I am suggesting this quantum computing here applications of that one. And then molecular structure analysis, a simple real-time examples of molecular structure analysis in quantum computing is the creation of new medicines. You can create new medicines. This is very helpful for new discovery of drugs and everything. So it will be speed up the process, and then it will be what I can say. Human life will be lifespan will be increased using of this technique, so that they can give faster solution for diseases and at all. So next, what am I trying to say in applications? Encryption. Encryption. Image. You can image. You are sending a private message to your team members. So traditional games keep the message safe by scrabbling it, but quantum computer could break that code quickly. We can use a lot of security purpose and different things, and then what I can say. Um, and then we can see this one, a quantum encryption technique use. And then the conclusion finally, what I'm trying to give means, my time is nearby over. What I'm trying finally give conclusion means quantum computing potentials. Quantum computing hardware promises to solve complex problems that are impossible, or impractical for classical computers. So quantum computing potential means it can give solve a complex problem solutions. You can give a real world impact. If a quantum computer give any real time solutions, we obviously give it real time solutions. What are problems means from cryptography and an AI to healthcare. This is because I told no already one COVID-19 based solutions it can give climate science. We can nowadays some forecasting, weather forecasting is it not be clear, but if you going for this one means we can give clear solutions for that. And then quantum computing has the potential to revolutionize the industries and tackle global challenges. We can give a lot of global problems have that global based problems. We can give solutions based on quantum computing techniques, and then collaborative progress, continued collaboration between researchers, companies, and government is essential to advancing quantum technology towards real world applications because of we need to do more R&D on that. In healthcare, how get the data set means we need to give data like how can I say in the form of data. If you going for image recognitions means skin disease based means we need to train the skin diseases like hundreds of images. One R&D we doing already like in healthcare using of machine learning. Snake bite will be on there. No snake bite. If a snake bite will be there means if they we taking going to a patient to hospital means the doctor they say asking the snake we need to see then only what type of snake will be bite will be to the human then only we can give a medicine for them. So that time we can go for like a machine learning artificial intelligence means what can we do means what can we do means the pattern we can recognize the pattern recognitions of the snake bite we can give a immediate solutions for the people there. If you go for very large data sets means we need a quantum computing that will be for analyze faster. So like that a lot of application in healthcare and all. So like that we need to do a lot of R&Ds. Here I what I need to say means the artificial intelligence will be get a big growth after coming of quantum computing because of we are in initial stage only in artificial intelligence. After coming of hardware, we need a best hardware because of still what will be happen means Nvidia. You can take a Nvidia. You can take a Nvidia company. Nvidia. Um, Nvidia company, yeah, whenever 1980 and 1990, Nvidia company they started for a graphic processing unit. The graphic processing unit, what the main thing of the graphic processing unit means, they need to work the gaming properly, smoothly. That reason only they developed the graphic processing. They need to design for gaming simulation and they need to work properly. But what happened after 2010, the 2010, 2015, after what happened, the Nvidia company share value will be increased because of AI demand of AI. The AI need to support the best hardware. In the nowadays, the best hardware AI to support Nvidia based boards only. So the company value will be increased. So it will be most biggest companies comparing to Microsoft, Tesla. The share will be more than that companies. Within a 10 years, they actually this changes because of demand of AI. They needed a best hardware like Nvidia. What I am saying here means in future what I can say the quantum computer after coming of quantum computer the AI will become a biggest it will be achieved. So the AI will be achieved. So finally, what I'm saying here means thank you for all for your time and attention today. So I'm truly grateful for this insightful questions and discussions we have had. You can give your interest and feedback to for me, and then thank you.
Thank you very much, sir, for your engaging section on quantum computing hardware architecture and components. It's really very interesting. Thank you so much, sir.
Thank you, sir. Thank you, sir. So give some about this section feedbacks. That will be very useful for me.
Sure, sir. Sure. So we will share it.
So can I leave, sir? Any
Sure,
doubts?
sir. Sure.
Yeah.
So dear participants, so submission of daily feedback is compulsory. Minimum 80% of attendance is mandatory to receive the certificates. So once again, participants are requested to submit daily feedback after session. So the minimum 80% of attendance is mandatory to receive the certificates. So I'm very happy to welcome the next resource person. It's my absolute honor to privilege to extend a warm welcome to Mrs. Letty Wakumaturi, the head of the Department of Computer Science at Bidolo University, Ethiopia. So Mrs. Letty Wakumaturi is not only a dedicated academician, but also an active advocate for community services. She has made a remarkable contribution to the field of artificial intelligence, having published several impactful research papers that continue the shape of advancement in the domain. So her passion for advancing technological education is truly inspiring. So evidenced by the workshops she has organized and app development, computer graphics, and web development, empowering the learners and innovators alike. Today, we are privileged to have her expertise on highly relevant and exciting topic, programming frameworks for quantum computing, physics, and quiz. On behalf of everyone present, I am warmly welcome Mrs. Letty Kwam Twari, and we are eagerly look forward to our learning from insights. Welcome, ma'am.
Okay, thank you very much. I will start.
You can share your screen.
Yeah. Visible, right?
Yes, ma'am.
Yes, ma'am.
Yeah.
Visible. Give full screen.
Uh,
Yes.
My name is Letty Wakuma. I am working as a department head in the Department of Computer Science under College of Engineering and Technology in Damdolo University, which is located in Oromia region of Ethiopia. So before starting my presentation, I would love to appreciate and thank P.S.V College of Engineering and Technology Chairman, Principal, and coordinators for providing me such a wonderful chance. So from the future quantum computing and high performance computing effective topics, ours will be, or the next what we are going to see will be programming frameworks for quantum computing, specifically Qiskit and Cirq. So it is more related to programming, or it is all about practicing what you have learned by using those frameworks. So that is why I hope all of you enjoy and learn a lot of stuff. And I hope you will get a good out of this presentation. So let us get started. So those are outlines we are going to discuss on. The first one is introduction to quantum computing. So I know you have been learning for the back 2 days, including the session before this one, introduction to quantum computing, but we need to overview the basic or core concepts that we need to retouch in order to write the program, or in order to deal with those programming frameworks. So that will be the first presentation that is going to take 5 up to 10 minutes. Then we will discuss about the programming frameworks. So we will define the frameworks from computer programming perspective. Then after that, we will deep dive into Qiskit and then Cirq. Then after investing our time learning the best thing out of those two frameworks. We will make the comparative analysis. We will discuss the difference between those two frameworks and their similarities. And also we will touch how we can use those frameworks or where to start. That will be the things we are going to discuss under this topic. Then after that, the future direction in quantum programming will be next. So after discussing those two basic frameworks, we will see the basic outcomes of those Qiskit in the circuits, which will direct to the future. So it is more related to AI or machine learning. So with the current quantum programming capacity, we will see through the future. That will be the other thing we are going to discuss. Then we will conclude the session by overviewing what we have discussed, and then the last slide will be dedicated to the resource. That means I will share resources that encourage you and help you to learn those two frameworks. Since we have limited time, we cannot fully discuss about those two frameworks, right? So I'm going to give you the resources that one will be the last. So let us start discussing. So the introduction to quantum computing is all about the concept of quantum mechanics, because when you say quantum computing, it is different from the classical computing because of the idea behind quantum computing, which is quantum mechanics, right? So with the use of quantum mechanics, or by gating, or the principle of quantum mechanics, we are going to have a new computing, quantum computing. So one of those principles is superposition. I am quite sure that you have discussed this one. So when you say superposition, it is about having a qubit in two states simultaneously. That means in the classical computer, we know information will be represented by using bit, and bit can be either 0 or 1. So in superposition, or in the quantum computing, the qubit, quantum bit, will be represented by using two states. And when we say state, it means there will be two values at the same time. I don't know if you have Googled about this quantum computing or about the superposition, or it is mentioned by other presenter. The best example for this superposition is spinning a coin. So when you spin a coin, it will have two values at the same time while spinning. That means there is head and there is tail. So this is what we call the superposition in the quantum computing. This is the first one. Then the second one is entanglement. This is qubits can be entangled, meaning their states are correlated no matter the distance between them. They can be correlated, and these can play a crucial role in the competition, in the effectiveness of performing computing using this special computer. This is the second one. Then we have quantum interface. So quantum states can interfere constructively or destructively. I hope I can show you this by using a graph. So this quantum interface is one of the basic techniques that can be used in the noise and error mitigation. You have learned that those quantum computers are sensitive to the noises. So with the use of quantum interface techniques, those things can be overcome. This is another principle in the quantum mechanics. Then the other one is measurement. So we've said that a qubit can exist in linear combination of two states. So that means those those status can be, those qubits can be 0 and 1, right? That is what we have said. So when it comes to measurement, it means when they are having two simultaneous status, the basic states have to be closer to one. Just yeah, it is possible they can have two status, but at the end it have to be status to one of those 0 or 1. So for that purpose, we need to work with probability. So quantum mechanics is actually, it depends on probabilities. So that is, there is no exact 2-point state. That means we have to measure the probabilities, and this will be discussed in detail in the framework. So I think this will be enough for the measurement. Then there are key concepts we need to know in quantum computing. So the first one is qubit. So we have mentioned about these qubits before, right? When we say superposition, it is we define superposition as qubits have two status, 0 or 1. So when we say qubit, it is analogous or parallel to the classical bit. So in the classical computer, we say bit, right? So in the quantum computing, we say qubits, and they use quantum status since they have two values. And the physical implementation of those qubits can be photons, trapped ions, superconducting circuits, and etc. And the second one is quantum gates. So in classical computer, we have bits, and by using bits, we can build gates, right? We have logic gates, you know, or gates, NOT gate, and the gate, right? Those are logic gates we use in the classical computer. So parallel to that, those quantum computers have quantum gates, and they used to perform different operation on qubits. And as we have listed out example for the classical logic gate as AND or NAND, we can list out for the quantum gates as Hadamard gate or Pauli gates. So this is the other concept. Then we have quantum circuits. So you can see how those things are listed down, right? So we have qubits, we have quantum gates, we have quantum circuits. So those quantum gate is about performing operation on qubits, right? So you have qubits, then you have quantum gates, which will be operated on qubits, and then you have quantum circuit, which will be built from quantum gates. This is the hierarchy between them. So by using sequence of quantum gates, a bunch of quantum gates, you can build quantum circuits like the classical computer. So those three concepts are pretty much related, or one is input to other. And the last one is the quantum speed up. So we are learning about the quantum computing, and we are investing our time, energy to learn this thing because it can play a crucial role in overcoming shortcomings of the classical computer. That means I know, I don't know if you know about the Morse law. There is a Morse law in which the speed and the size of computer can be estimated or defined every 2 years. That means every 2 years the transistor or the capacity of processing will be increased and the size will be decreased, right? So after some point, or after some years, that can be 5 or 10 years or 2 years, we have no clue about that, but those classical computers can go to the end. That means there will be a phase when we cannot minimize the size and maximize the processing. So let me take one example for this one. You know atom, right? We know atom. We have learned this concept in chemistry. So the atom cannot be subdivided, right? So the idea behind proposing those quantum computing is also the same. That means there, after few years or after a bunch of years, those classical computers come to end, or the Morse law cannot be true after a bunch of years. So for that purpose, this quantum computing was proposed. That means to make the computer make the instruction to executed exponentially. So this is what we call the speed up. And the other thing I want to underline is here, it says a quantum computer solves certain problems, right? So it is nothing quantum computer can solve every problem. It states that certain problems. That means not every problems are being solved by the quantum. So we can see the answer for this one later in other slides. So when we say speed up, it is about having the quantum computers exponentially faster than the classical computer. The basic idea behind having this quantum computing. Then let us discuss about the quantum gates, because later we will write those gates within our code. So the first one is known as Hadamard gate. This one is about putting a qubit in equal superposition state. When we say superposition state, which says that it is about having a qubit in two simultaneous states, right? We have 0 and we have 1. So we can put a qubit in the superposition state by using the Hadamard gate. And the second one is known as Pauli's gate. This one is similar to classical NOT gate. So in the classical computer, if you have NOT gate, then if it is 0, it will be turned to 1. And if it is 1, it will be turned to 0. So this is prior to the NOT gate. This Pauli's gate is used to flip the state of a qubit. And you might wonder how this Pauli X gate functions. So the concept behind this Pauli X gate is it is about having a rotation around X axis at 180 degrees. That is the concept behind the Pauli X gate. And the second one is Pauli Y gate. So here is the difference between Pauli X, Y, Z, in addition to what is written on the slide. So in the Pauli X gate, the rotation will be around X axis in the at 180 degree, and Pauli Y gate, the rotation is around Y, and Pauli Z gate, the rotation will be around the Z axis. So while those operations performed, then some change will be done to the status, or to the qubit status. So that is it. So the Pauli Y gate is similar to X gate. So it introduces what we call the phase shift. We have the shift of a phase. That means it's a swap, 0 and 1. Just 0 and 1 will be swapped in the Pauli Y gate. And the second one is Pauli Z gate. This one introduces a phase flip, and a phase flip which is only going to be applied to 1. If it is 0, the flip will not be operated on. That is the Pauli Z gate. And the fifth one is CNOT gate, which is abbreviated as CX. So this one is special since it is applied to 2 qubits. One is for the target qubit, and the other one is for the control qubit. So the value will be identified depending on the control qubits. So these ones will be also discussed later. And this CNOT gate is commonly used for creating entanglement. So there is one thing I haven't mentioned about the entanglement. When we say entanglement, it is about correlation between qubits, right? So we are not talking about a single qubit. If you are talking about a single qubit, then that single qubit can be visualized by using block sphere. I hope you know about the block sphere, which is used to visualize a single qubit. So that is not the same with the entanglement, since it is about the correlation between 2 qubits. So this can be done by using the CNOT gate. Then the sixth one is the phase gates. So these gates apply a phase shift to state. It introduces shift between 0 and 1. This one is also a shift, and unlike the previous one, unlike the Y gate, it leaves the 0 state unchanged. The phase shift will be applied to only 1. So those are few gates with their functions. There are also other gates. To overview, I hope those are enough, and I will discuss in detail in the coming slides. Then the other one is the quantum circuit. So we have qubits, then we have quantum gates, and with the use of quantum gates, or with the sequence of quantum gates, we can have quantum circuits. So the quantum circuits which manipulate their quantum state to perform computation. So they are basically the foundation of quantum algorithm, similar to the classical one. So the components of quantum circuits, just we have discussed this: qubit, quantum gates, classical registers. Then we have measurement, the core one, and circuit representation. So how a quantum circuit works? How quantum circuit works? So this starts from the initialization. So qubits are initialized in the state of 0. So the initial value for the state, the qubit state is 0. And I hope you know this symbol, right? This one is for Kate, and that is used to show the quantum qubit state. Then the second one is application of gates. So gates transform the quantum state of qubits, and also they can introduce the entanglement, and we have also what you call the measurement. So the measurement will be done to extract classical result. So two states are there. The classical result to one state will be done through the measurement. Then there are features of quantum circuits. The first one is reversibility. So quantum gates are unitary, meaning that they can be reversed, unlike the classical computers. Then the second one is parallelism. So multiple gates can operate on different qubits simultaneously. That is what we call the parallelism. And we have discussed about the entanglement, right? So multi-qubit operations such as CNOTs create correlation between qubits, and it will be essential for quantum algorithm. So what are the ecosystem of quantum computing? There are 4. The first one is hardware. So in the previous session, you have learned about the IBM, Google, IonQ, Rigetti quantum processor. So those companies provide the quantum processor. That means they have the hardware of quantum computer. So that is what they call the hardware. And then the next one is software frameworks. So software frameworks are a bunch. We have Qiskit, we have CIRC, and there are also other frameworks. So this Qiskit is proposed by IBM's quantum programming, by IBM's, and that is quantum programming framework, of course. CIRC is by Google's. Then the other ecosystem of quantum computing is simulators. So simulators are used to run quantum computers on classical computers to test algorithm, or even to learn how quantum computing works. So simulators are the one of the ecosystem. Then the other one is quantum cloud services. So in addition to simulators, there are cloud services that enable us to deal with the quantum computing. There is IBM, there is Google, there is also Amazon bracket. So from those ecosystem, you know, the topic is about the frameworks, right? So we are going to discuss about the software frameworks, and later we will link to the other ecosystem. So framework is actually not a new concept because it is already known in programming concept. And so we know React, right? There is a React that is ready to be to develop a web. So like that, or we can take that as a framework, and we can define a framework as a pre-built structured collection of code and tools designed to help developers create software application efficiently. So that is what the framework stands for. So with the use of framework, we can reuse our code. It will organize and make our code structured. Then also abstraction is possible, and there is also extensibility. So those are the definition of framework and the key characteristics of frameworks from computer programming perspective. So what are quantum programming frameworks? So we should start from definition. Quantum programming frameworks are software tools and libraries that allow developers to design, simulate, and execute quantum algorithms on directly the quantum hardware or simulators. So there is no difference between the the slide before this one and what written here. It is all about increasing reusability, abstraction, organizing, right? So with the use of those frameworks, we can design our own circuits. We can get to know the quantum computing, and also we can execute a bunch of quantum algorithms directly on the hardware or simulators. So having this quantum programming framework purpose is the first one is it is about creating interaction with the quantum devices. So it will simplify through those framework. Everything will be easy. So that is the first purpose. Then the other one is it provides abstraction layers for building and testing quantum circuits, and also it can bring the gap between quantum hardware and algorithm development. So those are the purpose of having quantum programming framework. So features of quantum programming frameworks. So what are features of those quantum programming frameworks? The first one is quantum circuit design. So we've said this before. We can define qubits, and then we can create a quantum gates to perform some operation on the qubit, and from the quantum gates, we can build the quantum circuits. Then we can visualize or optimize those created workers. This is the first one. Then we have what we call the simulation. So simulation is this about running, or it is about performing the computing operation on our computer, on the classical computer. So this is also one of the feature, and there is a framework which actually support noise modules, so that it can simulate the real world hardware or quantum computer behavior. Then the other thing is the execution. So with the execution, or when we say execution, it is about connecting the quantum hardware to the circuits in real environments. So it is to provide interfaces. And the last one will be algorithm libraries. So there are pre-built modules of common quantum algorithm in one of the frameworks. So we can really use those predefined or pre-built quantum programming algorithm. So it will make things easy. So let us discuss the quantum programming frameworks. The first one is Qiskis, which was proposed by IBM. So the feature is modular design with components for circuits, algorithm, and about the hardware integration. And the execution can be through the real device access or through the simulation. And the second one is circ. This one is actually the scope is tight when we compare to the QSKIT. So researchers and the developers focused on near-term devices. So they are mostly used for making experiments and research on the quantum programming frameworks. And it highly deals with a specific hardware, as in examples, Google's Sycamore. Then the other one is Penny. This one focused on the hybrid quantum classical workflows, and we can also have Microsoft Quantum Development Kit, also Q, which uses Q#, which is a domain-specific language for quantum programming, and emphasis on quantum error correction and scalable quantum systems. And the other one is Rigetti's Forest. This one provides tools for Rigetti quantum hardware. So, as you have seen on the topic of the session, quantum computing program frameworks, and we specifically specified QSKIT and the circ. So why we focus on the QSKIT and the circ? So let us see the strengths. So strengths of QSKIT is it is beginner friendly with modular design, and it is supported by the IBM ecosystem, and there are versatile applications we can do with the use of QSKIT. And when it comes to the circ, this one is actually related to the quantum hardware. It is about dealing with how this quantum computing works. That means it is mostly open for research and experiments, but it has advanced feature for the device-specific optimization. Since we said the scope is tight and that it focuses on the hardware. So we get to know about the hardware, that is the strings of circ. So, and they are widely used, and so we can directly access the quantum hardware through those frameworks. So we are going to focus on those two frameworks. Then the first one is QSKIT, right? So when we deep dive into QSKIT, so firstly, QSKIT is introduced by one of the well-known tech company, IBM, in 2017, and it is introduced as an open source for quantum computing framework. To complement the IBM quantum experiences. So it provides tools to build, to optimize, and it also help us in running basic quantum algorithms. So the usage of this QSKIT is designing quantum circuits, simulate quantum behavior, execute circuits on IBM quantum computers via the cloud. So design quantum circuit means we can actually create the qubit and then gates and build our own circuits. So that is possible. Then when we say simulate quantum behavior, just we can test, we can debug the circuits in our computer through the simulation on our computer without accessing the quantum device. And later, after practicing and after having the basic knowledge on how it works, in we can directly access the quantum devices. So simulation is not easy. You know, we really get to know the QSKIT through the simulation. Then the other one is executing circuits on IBM's quantum computers via the cloud. This is also possible. So let us discuss about the QSKIT architecture. So it consists of 4 key components. We have QSKIT Terra. So this one is the core library for building and running circuits. So if we are talking about circuits, if we are talking about how they build, that means we are at the low level. So the key features are quantum circuits, quantum gates, quantum backends, quantum transpiler. Then the second one is Qiskit Air. This one is high performance simulator, which says that one of the feature of Qiskit is having the simulate quantum behavior. So this will be done actually by using this Qiskit Air, and those are the features. That are enabled with the use of Qiskit Air, and the third one is Qiskit Agnes. So this one focuses on the quantum hardware. It is about the validation, about the noise, about the error. So we have the Qiskit Agnes, which is about the hardware. Then we have the low-level operation performed on the hardware, such as a circuit, that is Qiskit Terra. Then the last one is what? It is Qiskit Aqua. So this Qiskit Aqua is high-level module used for quantum application development. So it is about setting an algorithm. So I would like to give you some sort of classwork to work on this one. I have one question. So order those architecture according to their usage or according to their work, which says that we have low-level operation, we have the hardware, we have the simulator, we have the quantum application development. So can you order this? Just try this one while listening. The second one is Qiskit layer. So actually the answer is here. I hope I gave you 1 or 2 minutes. So Qiskit layer. So the Qiskit stack is composed of layers. So through those layers, executing can be enabled. Through these layers, simulation is possible. So let us discuss about the layers. Layer 1 is what? It is quantum hardware or devices. So it is about the physical quantum computer or the simulator we are using to build our circuit. So that is the hardware. Quantum hardware comes first. That is the layer 1. So in case of Qiskit, then the quantum hardware will be provided by the IBM MIS. So that is the first one. Then the second one is what? It is Qiskit backend. So backends are the interface between the Qiskit and the quantum hardware or simulators. So it comes between those two things. We have Qiskit, a programming frameworks used to deal with circuits or run algorithm, and we have simulators. Simulators or hardware. So between those, we have what we call the Qiskit backends. And then the third one, layer third, is Qiskit Terra. This one deals with low-level quantum circuits. So as mentioned in the first row, this one is about running circuits, about building circuits from the gates, defining qubits. That is the third layer. It includes those quantum circuits, quantum gates in the transpiler, and those can be used as a function while coding. And the fourth layer is Qiskit Aqua and Agnes. This one is for the application and error mitigation. So they provide tools for the quantum algorithm. So here we have discussed about quantum Aqua, right? So Qiskit Aqua, right? So this one is about dealing with the application development about the quantum algorithm. So this is the one concept on the layer 4. Then we have Agnes. So this one is about the error and the noise mitigation. So those one will be layer 4. This is what it looks like when we show it with the use of diagram from top to bottom. It starts from the Qiskit Aqua and Agnes. We have quantum application, we have quantum chemistry, quantum machine learning, and error mitigation. And then we have Qiskit Terra, and then backends, and then quantum hardware. So I want to mention one simple example. When we use our computer, there is the hardware, there is a system software, there is application software, and also talking of the software, we have programming software that's used to develop softwares. So those are four, right? We have listed out four of them. So you can merge those to the Qiskit layers. Like, for instance, we have computer hardware, through the system software, we can have the application software. You cannot install the application software without having the system software, right? So that is a best example. We can take the Qiskit layers, such like that. The Qiskit backend will work between the Qiskit and the hardware, like that. That is the Qiskit backend, like the system software of the computer, the classical computer. So this is about the Qiskit layer. Then the other one is Qiskit execution workflow. So how this Qiskit execution done? So we have to know the workflows. So we start from creating a quantum circuits. So when you say quantum circuits, defining the number of qubits is there, and then maybe applying the quantum gates or applying operation is there. Then after that, we will compile and optimize the circuit. So we use Qiskit Terra to optimize the quantum circuit for the target device, and we also use what we call the transpiration. And then after that, we have simulate or execute on quantum hardware. This one is for testing, debugging, and we can use, of course, Qiskit Air. And the last one is analyzing the result. So this is the good part of quantum computing Qiskit. You know, after creating your qubits and defining your quantum circuits, you can visualize through the use of histogram. So how to use Qiskit? Maybe I know most of you can wondering. So this is Qiskit, this is framework. So how can I practice? How can I write a code using this Qiskit framework? The answer is simple. There are two options. The first one is using IBM Quantum Workspace, which is cloud-based, and installing the Qiskit locally, which will be enabled through the usage of simulators. So when you say using IBM Quantum Workspace, it is about directly accessing the quantum processor through the cloud-based environment. So this one is currently discontinued starting from the March 2024. That doesn't mean the lab is totally closed down, but it is still allowed for researchers. And the second one is actually possible. We can install Qiskit in our computers, and then we can use the framework. So what are the steps we can take to install Qiskit locally? The first one is we start from the prerequisites. So sorry, I haven't mentioned this, but Qiskit use Python programming language. So if we are talking about Python programming, we have to install Python, right? So we will install Python, and here is the website from which you can download. And I recommend you to download starting from the version 3.8 or to 3.12. If you install the latest one, it's not going to be working for you, since it doesn't include this Qiskit. Qiskit is not added to the latest version. So when you install from version 3.8 to 3.12, and I recommend actually 3.11. So that's the first prerequisite. Then we will verify the installation by typing this command. I hope you are so familiar to this. And then we will install Qiskit. So to install Qiskit, like we install other Python libraries, we use pip install Qiskit. We will write like this. And then we can check either or not we have installed this Qiskit by writing the command import Qiskit. Then we will write this one. It will display the version if you have successfully installed the Qiskit, or otherwise some error commands will pop up if the Qiskit is not installed. Then this one is optional. It's kind of optional, but I highly recommend it. So it's installing Jupyter Notebook. We all know this. It is installed by using the pip command, and we type install notebook, and after installing, we will open by writing Jupyter Notebook in our command. So those things are done by using the command prompt of our window. Then let us discuss about the key function in QSkit. So the first one is quantum circuit. So it is written like this. QC is a variable. It is a variable. And we have quantum circuit. This one is the function, and or it is a method, and it takes how many parameters? 2 parameters. We have num key bits and num CL bits. This one is classical bits used to store the measurement results. So the state of the qubit can be 0 or 1, and after performing some measurement or after counting, we will finally decide the classical value of the qubits, right? So this is why we use these num CL bits. It is used to store the measurement, and this one is it is about specifying number of qubits in the circuit. Then there are qubit gates. So the first one is Hadamard gate. So to use the Hadamard gate, we write our variable created for the quantum circuit, then append to the H. This H stands for the Hadamard gate, and we will specify the qubit index. So when we say qubit index, it refers to the position of the qubit in the quantum circuit. So the position will be identified with the use of qubit index. And then we have poly X gate. So for poly X gate, we use X small. For poly Y gate, we use Y, and the qubit index will be the same. It is about, since it is referring the position of qubit in the quantum circuit. Then if we are going to use multi-qubit gates, for instance, if it is C node, controlled NOT gate, we are going to write as CX with small letter, and as we have mentioned before, it takes how many parameters? 2 parameters, right? We have the control qubit and the target qubit. So here is how the value will be identified. So if the control qubit is 1, if the control qubit is 1, then the target qubits will be flipped, and if the control qubit is 0, then the target qubit will be changed. So for instance, if you have 0 0, if you have 0 0, then the outcome will be what? The outcome will be also 0 0. Since the control qubit is 0, then the control qubit will be as it is, and the target qubit won't be changed as control qubit is 0. So this is how it works. I hope you have learned this before. So anyways, we can use this control qubit by writing the function CX and specifying the 2 parameters, control bit and the target bit. Then the other one is totally gate, CCX gate. This one have additional 1 parameter. We have control 1, control 2, and the target. So the target will be identified depending on the controls. Like the first one, by having additional parameter. Then we have QSkit execution. So let us discuss how it is going to be executed. So we have said before to write those QSkit framework, we have to specify. First, we have to select how to execute. We can use the simulator, or we can use the hardware, right? Actually, we cannot directly access the quantum hardware through the QSkit. So we are going to run execution on the simulator. So we start from circuit definition. We will define the quantum circuits in QSkit using the quantum circuit classes, and we add gates and also measurements. And the second one is back-end selection. So when we talk about the back-end selection, it is about selecting simulators from the QSkit air module. So we have mentioned about the air module, right? So we've said that it is used, it is one of the architecture, and that is used to deal with simulation. So for the simulator, using this air module is mandatory. And it can be Cosmos simulator, state vector simulator, or unitary simulator. So they are different depending on their functionality, and we are the one in charge to select them. Then there is what we call the transpilation. So transpilation is the process of converting high-level quantum circuit into an equivalent version that is optimized for an execution. So the circuit is optimized and compiled for the specific simulator backend to make use of the quantum computing effectively. This one is mandatory. So this one is about creating an environment. Then the other one is execution. So after specifying those things, we will execute, and the execute function run the circuit on the selected backend, either it is CAS or any other air libraries we can execute. And the last one is results retrieval. So we can view the results, and that highly depend on the simulators we are using. And when we say the execution on real quantum devices, the first one is circuit definition, which is the same with the first one using simulator. And then we specify how to access the IBM quantum platform. So we will log into IBM quantum account to access quantum devices. So the specific API will be assigned to us, and through that we can access the quantum devices. So this is the code we need to write. And if you are wondering what is the IBQ, it is the default hub for the general purpose to access. That means if we are using the keys for the general purpose, we can use this IBMQ, the IBMQ. Unless this specifically, unless you have a privilege to access the quantum device through research or your experiments, the hub provided for us will be the IBMQ, is the default one. Then we will select the backend. So in using simulator, selecting a backend is about selecting specific simulator, right? You have said CASMA, or you can specify other air simulator. So like that, in this one, we are going to specify the IBQM Lima, which is used to access a specific quantum device or simulator managed by the IBM quantum provider. Then the other one is circuit transpilation. So circuit transpilation is, as we have said, it is converting high-level quantum circuit into an equivalent version so that it can be optimized for execution on the hardware. That is why we use transpilation. And for that purpose, we are going to use what we call the transpile function. The transpile function, and we must specify the optimization level. So since transpilation is this about optimizing, right? And the other one is job submission. We will submit the transpiled circuit or optimized circuit to real quantum devices. There is a job submission, and here is the source, which is 1024. We will specify this in the coming slides. And then you have the job queue and execution. So this quantum device will be accessed by number of users, right? So here is what we call the queue. So the job queue will be there. So since it is shared resources, so our job can be placed in queue, and when it is altered, the execution will arrive, and monitoring. So since it is in queue and we have to wait for our turn, we can actually monitor the status of the job, what we have already submitted. So that is it. And the last one is result retrieval. This one is done using the histogram. So we have seen executing a Qiskit from two perspectives, or using two options, right? We can use simulator, or we can use real quantum device, even though we cannot currently access the quantum, the real quantum device. When we use the simulator, then we are using our computer, the classical computer, and when we use the real quantum devices, we are accessing the physical quantum computer. And when it comes to speed, the simulator will be fast, and actually it is dependent of the classical resources. And then we have the second one, real quantum devices. It will be slower. So if we have stated here, there is a job queue. Yes, we have to wait to share the resource. So the speed will be slower comparing to the simulator. The noise. So the noise in the simulator, we can have the noise. We can add noise. It is optional, and we can configure it to experience what having or accessing real quantum device looks like. But when it comes to real quantum device, it is intrinsic and unavoidable. And the other one is gate fidelity. In the simulator, it is perfect, and in the real quantum devices, it is limited by the hardware. And the use case is, this one is for testing and debugging. When we use simulator, is for the testing and the debugging purpose. And the real quantum device is for the purpose of real-world experimentation. So measurement in the results in Qiskit. So in quantum computing, as I've said before, the measurement plays a crucial role. It is used to extract the classical information from the quantum status, from the quantum state, which have two states. The classical have to be selected, which is single. So this will be done through the measurement. So as I have mentioned on the first slide, quantum mechanics or quantum computing is about the probability, and those probability have to be measured. So that is what the measurement standards in the Qiskit. It is due to the probabilistic nature of quantum computing. So we have to run the circuits, then we have to interpret the results. So after the measurement, the result is can be usually presented as a dictionary of outcomes, where the keys are the measured bit strings and the values or the quantities or frequencies of those results. Here you can see that we have two values, right? So this is the first one for state one. This one is for the state 0. These indicators, both 0 and the 1, were measured approximately half the time. This is why we have used 1024 shoots. That means it is repetition of the experiment as in the quantum, in the real quantum device. Those will be done. So making the number of representation or specifying the number of representation repetition is mandatory. And after representation, we can visualize the outcomes. So this is a simple program which can we map or which we can match to the hello world of the classical program. Here we start from importing quantum circuit, and we import execute, and we have to specifically import the Qiskit air. Before that, we have to install the Qiskit air by using the pip command, pip install Qiskit air. So that will be installed. After that, we can import the air, which is used in simulating. So this one quantum circuit will be used in creating a quantum circuit. This one will the execute is to execute, and then the air is to simulate. Then when we see the flow histogram, or when we import the flow histogram, so you know this one in machine learning, also plotly, those two are not new concepts. Just we have to import them from the Qiskit for the first one. They used to visualize the result. Then after that, we will create a quantum circuit. So here, how many qubits are created? How many qubits are created? One qubit is created, and this one is the classical bit, which is used to store the measurement. Then this is how to create a quantum circuit. Then after that, we do what? We will add a gate. When we add a gate, we will we can maybe apply the Hadamard gate, X gate, or Y gate. And as we have seen in the previous slides, we have to append the function by specifying with the parameter. So apply Hadamard gate to qubit 0. This is the definition for this one. And we can measure the qubit circuit by using the measure function. And for the simulation, we have specifically to write the type one. We will execute by calling the circuit, then the simulator starts, and then we can view the result. So when we say short, it determines how many times the circuit run, the repeated measurements to sample the distribution. Then the last one will be visualizing. After writing those codes, we can actually visualize what we have done here, what we have applied. We have created our circuit, and then we have applied the Hadamard gate, and then we can see the histogram, through histogram we can visualize the result. So there are pre-built algorithms in Qiskit. There are pre-built algorithms in Qiskit. So the first one is quantum algorithm modules. So there are pre-built algorithm in Qiskit, predefined algorithm in Qiskit. So you can use by calling the Qiskit algorithm. The one of them is the phase estimation. This phase estimation is actually a unitary operator, and that is used in quantum chemistry and Hamiltonian simulation. Then the second one is Grover search, one of the most well-known quantum algorithm, and that used to search unstructured databases. And here we can directly call from the Qiskit algorithms. Then the third one is the amplitude estimation. This is one of the quantum algorithm module. This one is to estimate the amplitude, as we have stated in one of the gates. Then the second pre-built algorithm in Qiskit is variational quantum eigensolver. This one is a kind of hybrid quantum classical algorithm. So they take the advantage of quantum and the advantage of classical, and that merges to make the best out of the algorithm. So this is it. And the core concepts in the variational quantum eigensolver is we have Hamiltonian, which deals with the energy of the quantum system, and that is highly used in the representing molecules. Then we have the variational principle. Then those four principles are related to the quantum energies. We have anastas, and those are actually visualized or can be symbolized by using the C symbol, as you can see from the screen. Then these are application of the VQE. Then the first one is it can be used in quantum chemistry, since we have already stated the Hamiltonian. The representing energy of the quantum system is highly used in the quantum of the chemistry. So this is the first one. So the other variational quantum eigensolver is condensed matter physics. It is used in modeling Schrodinger correlated system, and also it can be used in optimization problems. So you can ask what is the advantage of this VQE. The first one is the first advantage of variational quantum eigensolver is it contains the hybrid approaches, quantum and the classical. So this one can bring the good thing. Then there is a flexibility. Then there is also noise resilience. And there are also another algorithms in quantum algorithms that can work with Qiskit. So basically, without those frameworks, there are quantum algorithms, right? One of them is this Joe's algorithm, which is used to determine if the given function is constant or balanced with a single query. So the steps is we need to initialize, then we need to apply an oracle gate, then we need to measure output. Then this is how it looks like in code. We have to define the digital oracle as a function. Then we have to state the case. Here it is stated as a constant. Then the second one is global search algorithm. So we have specified this in the pre-built-in Qiskit algorithm, right? So without pre-built-in, it can be used as one of the quantum algorithm without specifying or calling out from the pre-built quantum algorithm. So the advantage is the same here. We have the oracle. So with the oracles and the diffuser, the finding an element in unstructured database will be enabled. The steps will be initialize qubits, and then we apply the oracle flip, then use the diffuser, then repeat and measure. So this is where it is used. Here we have the oracle flipping. It is flipped. Then with the use of the simulator, we can view the histogram. Then the other quantum algorithm with Qiskit is quantum phase estimation. So this one is used to estimate the eigenvalue or phase of the unitary operator. This one is actually key to many quantum algorithms. So due to the sake of time, I'm not discussing in detail as we have discussing before 30 or 50 minutes. Those are the real-world application of quantum algorithms. So the reverse algorithms can be used in cryptography, in searching problem, and the source algorithm. This source algorithm we haven't discussed, but this source algorithm is one of the quantum computing algorithm, and it can be integrated to the quantum Qiskit, or with the use of Qiskit framework, we can use the source algorithm, and that used for integer factorization, and the other one is TPE, which is foundation for the quantum chemistry. Then the other one is variational quantum eigensolver. This one is the hybrid. So this one is also used in chemistry. Let us discuss about the second one. So we have discussed about Qiskit, and then the next one will be about Cirq, right? So Cirq is an open source framework developed by Google Quantum AI, and it was introduced in 2018. And this Cirq is built to allow precise control over quantum circuits or quantum devices, the real quantum hardware. And it targets the noise intermediate scale quantum era. And one of the best thing is the Google made the Cirq the open source. It really encouraged us to engage in the research by practicing on the hardware. So this is the architecture of Cirq. So I have to mention something. We have discussed about the Qiskit and the architecture, right? So we are going to discuss about the architecture of Cirq. So there is circuits, there is gates, there is execution, there is optimization as in the Qiskit in both of them. Here, the difference is how they call the function, how they really execute within the code, how they use those functions. That is the difference between those architectures. So in the architecture of Cirq also, we have circuits and we have gates layer. So in this one, the basic layer will be defined. Gates will be defined. They can be X, they can be H, or they can be C0. Then we have the device-specific constraints. So unlike the these kits, we say that one of the basic functionality or one of the basic advantage you can get from Circ is it deals with the hardware, it deals with the specific constraints. So this is the second architecture of the quantum Circ framework. And the other one is execution layer, which is the same with the kit. And then the last one is optimization in the compilation layer. In the execution layer, it handles either the simulation or execution on the real devices, and in the optimization and compilation layer, it includes optimizing to get the best out of this hardware. So what is the design philosophy behind the kit? The first one is Pythonic approach. This one is the same for the kit. It is designed to feel native to Python. Just it is used the Python programming practices. And the second one is hardware agnostic. This one is, as we have said, one of the basic functionality of using Circ. And the last one is the flexibility. You can create custom gates, circuits, or also you can even schedule strategies. So what are the key components of Circ? So we have discussed, I've said this before, it is the components will be the same, but how they are going to be presented, how they are going to be used in code will be different. So the first one is qubits. Qubit can be different, defined in two ways, by grid qubit and the line qubit. If we are talking about the grid qubit, then it uses the 2D grid, and it is to reflect the layout of physical qubits in two dimension. Then here is how we can represent the qubit. We have how many qubits? We have how many qubits? 2 qubits. You might guess that as we have written before in the kit, when we write like this, we have two different parameters. One is for the quantum bit, and the other one is for the number of bits, and the other one is for the measurements. Right here, this one is, even though it is identified by using 2 dimension, it is about the location. This means 0 means it is located on 0 column, 0 row, and 0 column. We are talking about the 2D grid. And then Q1 grid qubit, here it is 0, 1. That means it is located on row 0, column 1. And the second option is using the line qubit. In this one, the qubits are represented or arranged in their linear topology. So that is it. And the second one is gates. So in addition to predefined quantum gates, the Circ allow us to define our own gates using the Circ frameworks. So that is why we can say it is more related to the hardware. So those are the gates. The difference between the kit and this one is in kit, the symbol will be X small, right? Here it is written by using uppercase. So this will be the same. And the other one is circuit. So we have first created our qubits. How many qubits are created here? How many qubits are created here? We have 2 qubits, right? Q not in the Q1. The first one is located in the column 0 in the row 0, and the second one is row 0 in the column 1. After defining the qubit, we have created a circuit by using the Hadamard and the CNOT. In the Hadamard, for the Hadamard, we applied the Hadamard to qubit 0. That means the value of the Q0 will be reversed, since Hadamard, Hadamard is about creating the superposition, right? If it was X, that means the value will be reversed. But Hadamard is about stating the superposition of the qubit. Then we have the second one, CNOT, the CNOT, which takes 2 parameters. The first one is for control, and the second one is for the target. And we have also identified or specified the measurement. And the printing is actually not mandatory. Then we have simulators. So we have to identify the simulators, like the Qiskit. So we have this function simulator, those runs we have called as the circuit you have created, and then repetition equals to 10. So you might wonder why do we need to repeat? Isn't going to take extra time? If you think like this, that you are correct. But you know the reason behind using the repetition or specifying the repetition in the assigning a value is through the repetition. It can be it is easy to identify noises from signals. So you know, quantum computers are, yeah, we have discussed this. Quantum computers are sensitive to noises, right? So through the repetition, we can identify, we can classify the quantum, I mean the signals from the noise. Then we can print the results. Then the other one is integration with the quantum hardware. So this one is for the simulator. If you are going to integrate to the quantum hardware, just we can use functions. So functions in the tools in Circ, the first one is optimizer. So in Qiskit, we have discussed about the transpilation, right? So in the Circ, we have the optimizer. So with the help of optimizers, the number of gates or the number of operations used during the definition of quantum circuit will be reduced. That means we will have fewer gates. If we have fewer gates, that means we will have less noises and we will have shorter execution times. So this having shorter execution times will make the quantum computer great. You know, this for this example, I can give simple example. Assume that there are two families, and those two families will get the same salary every month. Let us say they will take 100,000 rupees every month. So if it is going to be like this, that means, and if the first family have 5 members and the second family have 10 members, then which family have the qualified life or the qualified education or in the lifestyle? The family is a fair member, right? So this is the concept of using the optimizer. So optimizer will minimize the gates, and if you have minimum gates, the noise will be minimized and the execution time will be shorter. That means within nanoseconds, the execution will be performed. So this is the optimizer. Then the examples is here. Here we have used the mid-single qubit gates. So this is an example. We have used the optimized circuit and by merging single qubit gates, we can perform the optimizing. Here, when we say merge single qubit, you know, polygate, Hadamard gate, polygate. When we say polygate, it can be X, Y, or Z, and we can also have Hadamard gates. Those are single qubit gates. They take only one parameter, and that means 1 qubit. So we can merge these qubits, and then we can optimize. And the other one is noise merger. So this circuit allow us, the users, to define and simulate noise models by introducing noises into the circuit operations. So you might wonder, why do we need to introduce and to define noise, as the noise will minimize the quality of the execution? Yeah, the answer is, you know, in the real quantum computers, there is a noise, and with the use of specifying the noise models, it let us, the users, to understand and to prepare for the challenge while dealing with the quantum algorithm because of the noises. So if there is noises in the quantum real hardware, the quantum hardware, so in the simulation, having the noise classes help us to understand and to prepare for the challenges. And one of the classes is constant qubit noise model. And the other function is scheduled in the mapping tools. So we've said that schedule is pretty important in that Qiskit, right? We must have the schedule since there is sharing. So in this one, it is about restricting a qubit connectivity and scheduling the constraints in the through the schedule. So as you can see from the term, the term can answer the question. When we say scheduling, it's about using the time effectively, right? That is the purpose we are going to use this one. And there is also mapping. So when we say grade, or when we define the qubit as grade 0,0, which is about locating the qubit on column 0 in the row 0, it is not actually defined, or we are not actually talking about their location in the hardware until we map. So after mapping, just those definition will be mapped to the hardware topologies. So this is it. And the other one is visualization tools. Visualization tools also available either by using ASCII art or integrating libraries or through the graphical plotters. So let's get started with a basic circuit program. The first one is setting up our environment. So first, we have to make sure the circuit is installed, and to install circuit, the same to the Qiskit, we use the pip command, and we write the install circuit like is written on the slide. And then we can create our first circuit here. The circuit is created by using Hadamard gate, which is about applying superposition, right? So actually, how many qubits? 2 qubits says ranging to. So we have 0 and 1. So in Qiskit, Hadamard and also X gate, Y gate take only one parameter, right? And the parameter is the index. And talking of index, when we say index, like the index in array, here the index will be also starts from 0. It will be from 0. If you say range 2, that means we can access the qubit by specifying 0 in the 1. And we can print the quantum circuits. Then I have to specify this one. So while you install the circuit, it might fail because of the rust. So even though the circuit is Python framework, it is primarily written in Python, and it is designed for quantum computing tasks, like simulating quantum circuits, running them on quantum processors, and more. So this is about using the Python framework, right? However, some parts of the circuit and its dependencies use what we call the Rust. So without having the Rust, it might not be possible to install Rust. So I will recommend you to use this website to download the executable file, and then you will install, and then the circuit installation will work for you. So we've paused in the middle of the process, right? The third one is simulating the circuit. So we will simulate the circuit by using the function simulator, and we will append to the circuit, and then we can write the output the state vector, and also measurement is pretty important. Here also, when we say qubit, it is about superposition. It is about two states. And identifying or taking out of the classical bit is mandatory. So here also measurement will be mandatory, like the Qiskit. And we can run the circuit with the measurements after adding the measurements to the circuit. Then the last will be printing the measurement results. This is a simple program. Hello World program with circ. So we have discussed about every little thing on this code, right? We have discussed how to create circuits. Here, to use what? The grid. Qubit can be defined in two ways, by using the grid in the linear grid width by using 2-dimension. It is defined like that, but in this example, it is defined by using the second option. So this is the simple program, like hello program for the C++ or Java. So let us discuss about the quantum algorithm in circ. So we've said that circ primarily focuses on quantum circuit construction and the low-level hardware control, but at the same time it can support the quantum algorithms. There are variety of quantum algorithms. It can support them, but it doesn't provide a dedicated library which is pre-built like P.S.V. Those are quantum algorithms supported by circ. We have Jose algorithm, Grover search algorithm, quantum Fourier algorithm, quantum Fourier transform. We have Shor's algorithm, quantum phase estimation, and we have the variational quantum algorithm. So when you say quantum Fourier transform, the purpose is it is about computing discrete Fourier transform on quantum status. Then we have real estate preparation, quantum simulation. Those are algorithms. They are quantum programming algorithms. They are not quantum circ algorithm. They are quantum. They can be by circ frameworks. So it's time to discuss. I guess we have 3 minutes. It is time to discuss the key difference between circ and Qiskit. The first one is gate operation in the syntax. So you have seen about the syntax, right? For instance, for calling a function, one uses the lowercase one. So their syntax is not the same. The circuit construction focuses on moments on the circ, which group operations that occur simultaneously for the circ, and it emphasizes hardware native gates. It is about the hardware. So we can directly define operation. We can create our own circuits. Then when it comes to the Qiskit, it is the broader. That means rather than specifically dealing with the quantum hardware, it is more abstract way of building circuit by using the quantum circuit objects. And this quantum circuit object can support a variety of gates. Then the second one is hardware integration. So we have circ and we have Qiskit, right? We have talking about their difference. So in the hardware integration, when we say circ, it is primarily designed for the Google's quantum process like Sycamore, while the Qiskit is designed to integrate with the IBM quantum devices, but also supports other.
Sorry for the
backend.
interrupt,
So,
ma'am.
yeah.
So we seems
Okay.
we are almost out of time.
Okay. Okay. So I will finish within 1 minute. Sorry.
Sure, ma'am. You can continue.
Okay. So this is the basic difference. Through this table, you can see the difference between Qiskit and the circ. The similarity is they use Python. They used to run quantum algorithm. They used to run quantum gates. So those are the similarities. And as a general, I wanted to say one thing on the Qiskit and the circ. More of, since we are new to the quantum computing, it is advised to start from the Qiskit. The circ is mostly available for the research, for the experiments. So it is Qiskit is beginner friendly, and the circ is the research oriented or customizable. So the future directions in quantum computing, I guess you will learn those things in the future. The high level abstract interoperability, hybrid quantum classical algorithms, and the error mitigation in the techniques, fault-tolerant quantum computing. And there is also one thing about the specifying or having a program which will be easy to write or to deal with the quantum computing without having no background of the quantum programming or any specific programming languages. Those are the few things. So in the future, artificial intelligence, machine learning, cloud-based quantum program will be enabled. Those are the future direction in the quantum computing. As a conclusion, both Qiskit and the Cirq are powerful quantum programming frameworks. So the Qiskit have pre-built solutions, while the Cirq is better suited for the researchers and the developers. So I will recommend you to use to start from the Qiskit. So here is the resource. Actually, for the Qiskit, you can directly access the IBM website, and you can learn directly from there. So those are the resources. I will share the PPT with the organizer. So this is all about the presentation. If you have any query, you can contact me through my email ID. This is my email ID. I would like to thank you, all of you, for giving me your time and your time to listen. And I heard that today is a Christmas in India, so I want to wish you to have a wonderful day. A Merry Christmas. Thank you very much.
Dear participants, if you have any doubts or questions, feel free to ask. Dear participants, if you have any doubts or questions, feel free to ask.
Hello. Can you hear my voice, ma'am?
Hello?
Yeah.
Yeah, I can hear.
Yeah. Good evening,
Yeah.
ma'am. Ma'am, it is used to help to identify the plant leaf disease, ma'am. To identify.
Ma'am, can you repeat the question, ma'am?
You may type in the chat box. Any other questions?
Yeah, you can get the slides.
Hello, ma'am.
Yes.
How do you visualize the output, ma'am, after the code?
Uh-huh.
How do you visualize the output?
So visualizing is enabled by using the Python libraries such as MATLAB, and we can also visualize by using the histogram. I hope you know those visualizing from the machine learning and the quantum machine learning and artificial intelligence. So in deep learning, in the machine learning, we can visualize, right? So the same thing can here apply to the quantum computing. You have first you have to specify.
Okay, ma'am. But in machine learning and AI-based problems, we have some evaluation method to evaluate our output. Is there any specific evaluation method is available for checking the output of this quantum process?
Yeah. You can print the results. There is a function for the results which counts the probability of the status after the results. You can visualize here. It is written on the slide. You can recheck the slide.
Hello.
Hello. Hello.
Yes, sir. Your voice is
Yes.
audible.
Yeah, ma'am, I have one continuous question from the past questions. I like that
Okay.
in machine learning we say about the while doing the evaluation, we save all the results in some data frame or CSV, and we visualize those things using matplotlib and scikit-learn. But here in quantum, because we are not going to save anything in the format of rows and column. So how we will visualize that our performance is better compared to others? Did you got?
Dear participant, please
Okay, I think
mute your microphone, please.
I think the question is regarding visualizing. So I hope we have an extra time to even run the simple program. So it is in the slide. We have discussed this in the slides. I will recommend you to first review what we have discussed. Most of the questions are directly from the material. So view those materials, and if there is any additional question, you can email me. You can send me the email, your question through my email ID. Regarding the histogram, regarding the visualizing, we have said that we can use histogram or we can use the matplot, the library. So those things are already specified through writing the simple program. So first try those codes, and then you can ask. I guess those questions are raising because we haven't executed any program. We haven't seen any simulations due to the shortage of time. So I'll share this material after going through the materials. Just send me your questions through my email.
Thank you very much, ma'am, for the insightful and engaging section. It was truly informative and valuable. Thank you, ma'am. Thank you so much.
Thank you very much.
Thank you, ma'am. Thank you. You can
Okay.
left from the meeting. Thank you.
Okay.
Yeah,
Thank you
participant,
very
the
much.
feedback link is available in the chat box. Kindly take a moment to fill out the feedback form. Dear participant, the feedback link is available in the chat box. So kindly take a moment to fill out the.
Thank you, ma'am.
Thank you very much.
Dear participant, tomorrow day 4, session 7. So the resource person, Dr. B. Elilvanan, Managing Director, V Technology, Chennai. So day 4, session 8, resource person, Mr. Anjikia Lokare, CTO and founder, Ditto Security, Mumbai. Dear participant, the session will be start tomorrow by 6 to 7:30. Resource